Thanks a lot to the organizers for the opportunity to present our work here. So I'll be talking about our work with Andrea Guerrieri and Pedro Vieira on trying to incorporate multiparticle scattering amplitudes in the S-matrix Bootstrap program and using that to study confining flux tubes in Yang-Mills theory. So let me start by celebrating the success of a different type of Bootstrap by reminding you that by now the conformal Bootstrap has evolved into this framework which allows us to, in a sense, effectively solve many very generic conformal field theories. So by effectively solve, I mean that it allows us to sharply bound the most relevant observables in these conformal field theories. So for example, we recently released some state-of-the-art study of the Eisen CFT, which is an update of the very famous bounds from a few years ago on the sigma epsilon system. So in this study, we study the Bootstrap system for the spin energy tensor operator in the 3D Eisen CFT. And this allows us to precisely determine dimensions and structure constants of these operators to 9 digits. So in this sense, we can do precision physics for these strongly coupled interacting theories at this point. Now, for quantum field theories for which there's a presence of a mass scale, the dynamics can be much more complicated. And it seems to be very far away from effectively solving some generic non-perturbative theory. Now, in theories which admit scattering observables, one strategy to try to reproduce the success of the conformal Bootstrap has been to consider the scattering of light modes in this theory, for example, consider 2-to-2 scattering processes and require that these scattering processes are consistent with fundamental principles such as causality and unitarity. There have been many successes in this direction. For example, there have been bounds on effective field theory coefficients and on-shell couplings of hadronic physics, bounds on effective field theories of gravity, constraints on the outcome of a G flow. So for example, if you have some UV CFT and you deform it by some relevant operators, you can constrain interactions on some massive place for which it flows to. You can discover new exactly solvable S matrices in 2 dimensions, and so on. Now, this program is called S-matrix Bootstrap, and today I want to discuss the inclusion of end-to-end processes in the Bootstrap. Now, given all the successes from studying 2-to-2 scattering, I should give you a good motivation to study end-to-end. Can't we just keep pushing 2-to-2 all the way and learn all that we could hope for in quantum field theory just from that? And perhaps the best motivation I can give you for why we should really consider multiparticle processes is that often particle production is the dominant outcome of scattering processes, and so if you want to capture the dominant physics, you should really consider multiparticle processes. So for example, this is the case in gravity, where in many kinematical regimes we are dominated by emission of gravity waves, or at high energy colliders. Now, if our goal is to develop the S-matrix Bootstrap framework, we might say that starting by studying gravity or high-energy collisions is very hard, because these are very complicated systems. But particle production dominates even in some of the simplest non-perturbative quantum field theories we can imagine. For example, let's consider the 2D Ising model at above critical temperature and some small transverse magnetic field. So this is a very simple model. We start with the simplest minimal model in 2 dimensions, the Eisen CFT. We deform it by the energy operator, and then we deform it by the spin operator. So the first 2 terms just give massive free fermion. The mass scale is set by tau. And then we do a small deformation in the spin operator direction, where h is small in units of the mass. Now, this theory is very close to being a massive free fermion. However, Zamolodchikov has conjectured that particle production dominates at high energies for arbitrarily small magnetic field. And this has been recently observed by some nice real-time simulations with tensor network models, where they observe a complete inelasticity at high energies for arbitrarily small magnetic field. Okay? Now, another motivation to study multiparticle processes is that it gives us very direct access to very crucial physical properties of scattering amplitudes. For example, soft theorems in the case of theories of Goldstones, or factorization, or cluster decomposition, which are not accessible at the level of 2-to-2 scattering amplitudes. And there are many other things, but I want first to discuss a more concrete and quantitative motivation to study these processes in the matrix bootstrap, which is to consider what's arguably the simplest matrix bootstrap question we could ask, which is the following. So let's consider a two-dimensional massive quantum field theory with a single stable particle phi of mass m. The question is, how big can the on-shell cubic coupling G phi 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 be in units of the mass? It's a very simple question, and one can try to at least place a bound on this cubic coupling by requiring that the 2 to 2s matrix is unitary, cross-symmetric, and analytic. This is the answer. In fact, we know the unique 2 to 2s matrix that saturates this bound. Yeah, the unique, that is, the unique S matrix that realizes this coupling, G phi phi phi, equal to this value. This is the answer. It's a very simple expression. Let's try to examine it in more detail. So recall that we are discussing two dimensions, so the only variable is the energy S, there's no angles. So the other monostall invariants are fixed in terms of S, U is 0, because you're always forward scattering, and T is 4m squared minus S. Now, this expression satisfies all that we could ask of an S matrix. It's unitary, it's a pure phase for S above threshold. It's crossing symmetric, it's manifestly invariant under S and T exchange. And it's analytic in the sense that the only singularities are the unitarity cuts, which are given by the square roots, and the cubic exchange at S and T equals m squared, which are given by the poles of this rational factor. So you see, this object satisfies all you could ask of a 2 to 2s matrix, and it realizes the coupling for which there are rigorous bounds that there cannot be anything bigger than that. So from 2 to 2, the game is over. There's an explicit S matrix saturating the bounds. But what I want to tell you is that even though that's true, there is no quantum field theory that realizes this coupling. And you could not figure this out from 2 to 2 alone. And that this S matrix is in fact inconsistent.
And looking at your S matrix, when S larger than 4m squared, it looks like there's no phase or something wrong.
There's an I here.
I, right, but S minus 4m, it will be positive, right?
Yeah,
sorry.
No problem.
Yeah.
So, and to see that, we need to analyze the multiparticle amplitudes. So let's consider 2 to 3 amplitudes in this system. Now, generically, the 2 to 3 amplitude will have singularities. In particular, it will be singular in the limit in which P1 is equal to P3. So this incoming moment of P1 is equal to this outgoing moment of P3. The singularity comes from two related on-shell processes or diagrams that are associated with singularity. First, the single particle exchange, and second, this triangular on-shell diagram, where all internal lines are on-shell. It turns out that both of these diagrams contribute to as poles in 2 dimensions. The residue is the following. The single particle exchange has a residue proportional to the cubic coupling times the S matrix evaluated at energy or Mandelstam S12, the incoming energy here, while the triangle has a residue proportional to the cubic coupling times 2 factors of the S matrix evaluated at S14 and S15. Now, I'll soon argue that there's an inconsistency unless this residue vanishes. But this residue can only vanish if the S matrix satisfies this equation. And it turns out that the optimal S matrix from the last slide does not solve this equation. And now I'll argue that this leads to an inconsistency. Since the S matrix does not satisfy this equation, the residue does not vanish, which means that the 2 to 3 amplitude cannot be 0, which means that the probability of 2 particles scattering to 3 particles is not 0, which means that the probability of 2 to 2 must be smaller than 1, but S optimum is a pure phase, and so this is a contradiction. So this S matrix and this coupling are excluded, and so even in this very simple bootstrap question, multiparticle consistency seems to play an important role. Now, of course, it's very hard to develop a general bootstrap framework for multiparticles because these are very complicated objects. So the goal here is to try to find the simplest setup which allows us to impose some form of analytically tightened crossing for multiparticle processes. And fortunately, we don't need to go all the way down to something very boring. It's still a very interesting setup, and this setup is the one that Victor introduced yesterday, I think, which is that of confining strings. So the goal would be to constrain the dynamics of polar flux tubes using multiparticle symmetry bootstrap techniques. So let's consider some long flux tube in, say, pure SUN Young Mills in D equals 3 or 4. We can source such long flux tube by considering, say, 2 Wilson loops that are wrapped in some compact dimension, and then taking this dimension to be very large, so we are back in flat space. Now, the low energy excitations on top of this flux tube are massless, as Victor reviewed yesterday. They are nothing but, they are the transverse modes of the string, and they are nothing but the Goldstone bosons from the breaking of the bulk Poincaré to the presence of the long string. We break it from d-dimensional Poincaré to Poincaré on the worldsheet times transverse rotations. We'll focus today on D equals 3, for which there's a single Goldstone mode. But we could totally generalize the techniques to D equals 4 by keeping track of some flavor index. Now, the low energy dynamics of these Goldstones is governed by effective field theory. We can write the most general action that's allowed for these Goldstones by reminding ourselves that the action must be invariant under bulk Poincaré, and so it can be expressed as an expansion in curvature invariance. So to lead in order, we have just the Nambu-Goto action, the area of the flux tube, but then there are higher order corrections, Ricci, k squared, extrinsic curvature, k to the 4, and so on. The effective field theory is an expansion of energies over or times the confinement scale, or the string length. And as I said, the first term is just Nambu-Goto action. And this determines the dynamics at low energies, but at energies of order inverse string length, the effective field theory breaks down and the theory becomes strongly coupled. And our goal will be to constrain the physics of, in this regime. So we'll do so by considering the scattering of these Goldstones on the flux tube. Now, this should immediately raise alarms, because I'm talking about considering the scattering of massless particles in 2 dimensions. So you might worry that the envelopes are plugged with infrared divergences, and you might wonder if this matrix is even a well-defined concept in this context. So let's first try to address these worries. Well, another worry is that, you're in 2 dimensions. You have massless particles that are either left or right moving. So if you imagine you have a bundle of, say, right movers, they move collinearly and they never separate. So you might worry that they never stop interacting, and you don't even have some nice asymptotic Fock space. So how does this work? So let's consider a bunch of isolated right movers. And let's ask how they interact, or how do they self-scatter in the absence of left movers. Now, from boosting variance on the worksheet, we know that this right S matrix can only depend on ratios of the external momenta. Now, ratios of external momenta are energy independent, energy scale independent, which means that we can evaluate this S matrix at any energy scale we choose. In particular, we can evaluate it at low energies. Now, at low energies, we can evaluate everything in terms of the effective field theory, which depends only on derivatives of the transverse coordinates. So the Goldstones are derivatively coupled, which means that all interactions come with powers of momenta, and so the theory is free at low energies. Now, combining these 2 facts, we find that actually isolated right movers don't interact. They are free particles. As a consequence, the asymptotic Fock space makes sense despite having massless particles in 2 dimensions, because they're effectively free particles. And in fact, the S matrix is well defined and free of infrared and collinear divergences, which of course is something you can check with explicit effective field theory perturbation theory. Now, having discussed so the right and left scattering is trivial. Now, having discussed the left and right scattering, let's discuss now the non-trivial dynamical part of the S matrix, which are the left-right scattering. So we'll consider a bunch of particles that are scattering. They'll have some total incoming momenta, right-moving momenta PR, and some total left-moving incoming momenta PL. Let's say that there are n incoming right movers here in this bundle. and we're going to divide this total momentum PR into any particles, and we'll parameterize this part of the state by specifying the energy fractions. So, for example, we say that we have energy fractions beta 1 to beta n, which means that the first particle, P1, has momenta beta 1 times the total momenta PR. There's an R index missing here. And of course, the sum of our energy fractions for physical configurations must sum to 1, and they must all be positive. So what we'll do is that we'll scatter some so-called jet states. So define a discrete basis of states by integrating these bundles of incoming particles against wave packets at fixed total momenta, but we're going to integrate it against wave packets in the energy fractions. It's not so hard to uncover what's a complete discrete basis. And let me emphasize, this is just a change of basis from definite individual momenta to essentially normalizable states up to the momenta, total momenta. And so the S matrix of these so-called jets contains the full information of the N2M S matrix at physical kinematics. Now, we choose these wave functions and normalize them so that the overlap of these states, so they're normalized just like one particle massless states, okay? Now, notice that kinematically, these states, they transform under Poincaré just like other one particle massless states. So kinematically, they're somewhat indistinguishable from the fundamental Goldstones. So from Wigner classification, you even say that they are one particle states, only that they now carry this effectively infinite dimensional flavor index, which specifies this jet wave function. So our strategy will be to consider the 2-to-2 amplitude of these jets, and because of this kinematical fact, we should expect that they are indeed, that their amplitudes indeed satisfy the same analytic cross and unitarity properties of the 2-to-2 amplitudes of individual Goldstones, where we now need to treat these jet wave functions as an additional flavor index for S matrix. Now, note that by imposing the cross-analyticity of these jet amplitudes, we're imposing some, but not all, of the cross-analyticity properties you might expect for the full N2M S matrix. So in particular, we are exploring analyticity in the total energy S, but not on the energy fractions beta I. We are crossing, we're doing crossing moves where we cross all the left movers or all the right movers at once, but not individual components inside the jets. However, we are capturing the full unitarity if we consider all jet states, because we're just doing a change of basis. Okay. Now, let me discuss some concrete computation. So we'll actually do numerical asymmetric bootstrap, so we need to consider some finite system of amplitudes. And so what we'll do is that we'll consider the minimal setup where we have the fundamental Goldstone and this simple two-particle jet state, which is this blue line, which is given by integrating this two-particle state against some wave function. And we'll consider all amplitudes that you can make out of these two new particles. You have the 2-to-2 process, and then you have 2-to-4, 4-to-4, 3-to-3, and 3-to-3 reflection, where, again, we need to understand that in this multiparticle process, we are projecting these lines against these wave functions. And we don't have 2-to-3 and 3-to-4 because we have some Z2 symmetry, namely parity in spacetime, which says that the Goldstones are Z2 odd. In the future, one can consider a bigger system with more and more jets and so on. There's no obstructions other than computational obstructions. And then the basic constraints take the usual form. So crossing becomes a simple linear relation between amplitudes. Unitarity becomes a semi-indefinite constraint. And analyticity takes the form of some simple subtracted dispersion relations. So we can impose these constraints and ask for bounds on various observables. And I don't want to emphasize the numerical methods, so for today we will just assume that everything is done analytically, which is approximately true. So then I should discuss what observables can we bound. And let's recall that our goal is to understand the dynamics at energy scales of order 1 over string length. And so a natural set of observables to consider are some kind of effective couplings, where we measure this S matrix with flavor index labeling the various jets at some energy scale S star, where S star is taken in the upper half plane, where the S matrix is analytic. These observables can be expressed in terms of physical values of the S matrix through dispersion relations. And so we'll choose today to determine some allowed space for this effective 4, 8, and 6 particle couplings defined in this way by just evaluating the S matrix at S star, and we'll take S star to be I over the string scale. Now, what values can X, Y, and Z take? So here are the results. So if we just impose analyticity, unitarity, and crossing, we get this blue solid. So the axes here are -1, ranging from -1 to 1. And we get this very generic shape, which should apply to any massless theories into dimensions for which the S matrix is well-defined and observable. Next, we can try to impose some actual flux tube physics. So how can we do that? The first thing we can do is impose some effective field theory constraints. So we ask now that these various S matrices, they are given by the prediction of effective field theory up to a given order in energy. So in particular, up to order S squared, all amplitudes are given just by the Nambu-Goto action, and this is the prediction. And when you do that, you find that now X, Y, and Z must live inside this red solid, which is about 100 times smaller in volume, or 5 times smaller in linear dimension. Now this result suggests you an idea. Let's just impose more and more effective field theory constraints, and then the bounds will shrink more and more and more, and we'll celebrate. So, well, again, this is the action. And we consider all that we could compute using just Nambu-Goto. To go to higher orders, we need to include these new operators. Now, it turns out that the first two, one is a total derivative, the other vanishes on shell, and so they don't contribute to scattering amplitudes. So the leading correction to the previous prediction is that the symmetries are all parameterized by a single parameter gamma, controlling k to the 4 up to order s to the 4. For example, the 2 to 2s matrix is given by this expression up to this order. So we impose that, and we find that this idea fails. The bounds actually do not improve as we impose more and more effective field theory constraints. And this idea fails in an interesting way, because you find out that to realize the previous bounds, you must have that these Wilson coefficients, they grow as you approach the optimal bound. So only for very, very large Wilson coefficients can you saturate the previous bounds. But this is very unphysical, because the physical theories of interest, they have an effective field theory that does not break down at arbitrarily low scales. And in fact, physical theories have very small values of gamma. For example, Lattice has measured that for the SU2 and SU3 gauge theory, these are the values of gamma. So this suggests for looking for bounds on these effective couplings, assuming that gamma is small. I spoke very fast. And when you do that, for example, assuming that gamma is smaller than 0.7, which is, in philosophy, similar to imposing a gap in the conformal bootstrap, if you're familiar, you find that now these parameters x, y, and z must live inside this tiny, tiny island, which is 100 times smaller in linear dimension than the previous bound. And so in this way, we can determine these observables to 3 decimal places. So here are some conclusions. We can interpret this result from this matrix bootstrap as determining some finite energy observables, Lorentzian observables, in the flux tube theory with small error bars, given some very minimal physical inputs that the EFT coefficients are small. Now, not being limited to just to 2 scattering, it seems that this confining flux tube is the simplest S matrix bootstrap one can consider. And so the dream here is that we can go all the way and effectively solve string dynamics in various confining gauge theories. Of course, this is a very hard problem, and we're very far from solving it. And so in order to move towards this goal, we should input all other physical constraints that we can think of. So for example, some of the things we haven't even touched on are, say, soft theorems, or open-closed duality, the fact that at high energies, physics should be governed by perturbative Young-Mills, or say high energy sum rules, and also the plethora of other lattice data that's available, since so far we only inputted some statement about the magnitude of effective field theory coefficient, which proved to be very powerful. So many of these are work in progress with John Albert, and I hope to have an update next time. Thank you.
So thanks very much, Alexander. I have a question here.
Could you use this, for example, to see the axion in 4 dimensions?
Right, so another future direction is to reproduce this exercise in 4 dimensions, study what's the impact of particle production on the physics of the axion, or include the axion in the Bootstrap system, and so on. And this is certainly something I want to investigate, but I'd like to first do this, and then once I have this, I can go and do this in 4 dimensions and do everything together to do a more phenomenologically oriented study.
But is the axion a stable particle?
It's not a stable particle.
So then you need to treat it a little differently, right? But I was wondering if you could do 1 to 2 where you sort of weakly couple something in from the outside.
Yeah, there's a study by Victor on the axion more carefully.
Uh-huh.
In this original paper by on Flux-based matrix Bootstrap by Pedro and others, they saw the axion as a sharp resonance, and it was consistent with the lattice measurements. And then with Andrea Guerrero, we did some more detailed study on this axion pole, but that was just 2 to 2. So indeed, if with his technology, we should get it more precise. Yeah, but there are also, they have this way of doing like some form factor bootstrap. So then I think you can potentially include it as some sort of, some axion form factor. Yeah, so this, can I ask a quick question since I have a microphone? You said that you can only cross all the left movers at once, but why can't you cross one of the left movers and then some amplitude between your jets of different flavors should also be related by crossing?
Okay, so then I need to discuss crossing a bit in more detail. So it turns out that crossing for multiparticle processes is a bit more complicated than what we think naively. So, for example, these authors have argued that crossing for n-to-m amplitudes takes the following form, and he'll illustrate in an example. Suppose you have this 4 to 4 process. If you cross 1, 2 into 5, 6, generically, what you land is not on the asymatrix, but on this object, where you need to insert the asymatrix conjugated on all of these bundles, and then you need to sum over a complete basis of states in the middle. Now, this is not an issue for us because, as I told you, if 7, 8 is, so if each of these bundles are purely left or purely right movers, we have this identity, which I argued for, and so indeed we recover the naive asymatrix. So it's consistent with what we are saying. However, here. No. Here. So if you try to cross inside the jet, naively say, okay, now this will mix my various jet states, but yeah, that's the true statement, but it will be a very nonlinear relation between the asymatrices. In particular, yeah, it will be cubic. It's way beyond the framework of semi-definite programming. It involves infinite many objects right away, and so on. Thanks.
Just comment to the previous. You said that this using the sum rules, for example, here at the conference is Martin Kruzhensky, who actually, I don't know if you know their paper, because of his collaborators, they using this addition to Bootstrap to calculate this pi, the calculate scattering, and that's actually good results this extended Bootstrap with this additional constraints. But I also have a question besides this comments that to ask you when you talk about this wave packet. No, I was thinking about as an example, like say, consider say mass is QED. Mass is in the sense that mass of electron goes to 0. Then, no, I mean it's again like a jet you were talking about, but specific distribution of say photon in the jet. It's not arbitrary. It should be a very special way, consistent with kind of QED. It's not. I mean, so there is some universal part in this kind of wave packet which should be there to take care. I'm not sure whether it shows up in your 1+1, but there it was important.
Okay, I'm not exactly sure what you were referring to, but maybe we can discuss that in more detail afterwards.
Sorry? Yeah. It's just a QED where mass of everything goes to 0.
Yes.
And that's also kind of that's.
Okay, there's some subtleties with this idea if you try to apply it beyond 2 dimensions, because here it was very crucial that particles are collinear, so that this jet effectively transforms the massless state.
But in QED, for collinear singularities, is very much similar.
The issue is that if you just consider collinear particles in higher dimensions, that does not define normalizable state, because to define normalizable state, you really need to integrate a bit on the separation between the photons. So.
It's still vaguely reminiscent of hard exclusive scattering in QCD,
Absolutely.
where there are these wave functions,
Yeah.
but yeah.
The picture is kind of there, but to
Yeah,
make it
no, I'm
sharp
not
is
saying
tough,
that
yeah.
you could use any of these crossing calculations. Other questions? Back here.
Thanks. I'm actually a little bit, so you're considering this non-perturbative as matrix bootstrap and try to constrain the effective coupling that you, but how is that coupling related to the low energy Wilson coefficient? I would think it's a sort of a bunch of compilation of all possible Wilson coefficients.
It's not directly related to effective field theory coefficients. It's related to really the S matrix at physical energy at all energy scales.
Yeah, but if you just take you have a full, now suppose you have a non-perturbative S matrix and you take the S goes to 0 limit, there should be a EFT matching to match to the low energy
Right.
EFT, right?
Right. So your question is, how does the effective field theory constrain the low energy?
Yeah.
Well, I mean, here's the action. You compute the amplitudes that follow from this action. You find that up to, for example, for the 2 to 2 amplitude, that up to order S to the 7, the amplitude is polynomial. And then beyond that, you might have logarithms and so on. But that's an exact statement. So the low energy expansion of this matrix is polynomial up to order S to the 7. And I can just read off matching between Lagrangian and the low energy expansion of this matrix.
Yeah, okay. Yeah.
That's a non-perturbatively correct statement. Yeah.
Just to continue that, does that mean if you make this gamma assumption and you shrink down into this tiny region, you get precise predictions for the polynomial coefficients? Or are they still allowed to vary?
Okay, so in the way that I defined, actually, I cheat a little bit because I already did this conversion. So the gamma that I showed you is actually the coefficient of the S cubed term in the S matrix.
Okay, so you made an assumption about one of them that is
right.
very small.
That's right, yes.
But then the other ones?
The question is, given that the assumption the gamma 3 is small, can gamma 5 be big, for example?
Things
the
like
answer
that.
is yes.
Okay.
Yeah.
Yes, very nice talk. I just wanted to ask you at the beginning, I thought you are doing finite n, so you can probably, if you put too many of these oscillations, create a closed string at some point.
Sorry, say again, please.
But I think you are doing finite n, at least, so you could, if you put many of these particles colliding, you may eject a closed string at some point.
Right, so for example, you can imagine that I also had other states in my Hilbert space, namely glue balls, for example, and there might be processes where I emit glue balls, and that's true. The whole idea right here is that all of these states, they contribute to the equations positively, and so I can still make correct statements by dropping out the states and replacing inequalities by inequalities, and I'm going again.
Maybe you said it. Do you see any pattern of resonances inside the region? No resonances.
No resonances. I see a very maybe sure. At the boundary of the space of allowed amplitudes, we see very intricate. There is a subtle here. So this is the kind of profile of the amplitudes at the boundary, for example, when particle production is maximally large. And you find first that the profiles of particle production are very non-trivial, and you do find also this breakdown of unitarity saturation in some channels. So it's not clear what the physical interpretation of this, but I'll not. Of course, it's not a resonance. I don't know.
Very, very nice talk. I'm wondering if you go to higher dimensions and massive particles, then usually the analyticity is attached only to the T matrix, and you have to separate the non-scattering piece. Do wave functions somehow allow you to get around this, or how do you get to higher dimensions with massive particles? That's my question.
If I knew, I would be given a different talk.
Well, I know, but I'm just saying that the general statement of analyticity has to separate out the singular behavior in momentum space of the free particles, right? And so there is no analyticity for the full S matrix in momentum space. And of course, momentum space states are non-normalizable, and they're not in the Hilbert space, and so on. So I can imagine there might be another way to go, but I don't see the connection.
Let me make a comment that this fact that the multiparticle S matrix has various pieces, some of which have more distributional support than others, is also true in 2 dimensions. And indeed, the fact that we're integrating against wave packets is hiding that away, because in energy things work out. Now, that's a true statement that could extend to higher dimensions, but it's not enough to make progress there.
So in Xu Heng's colloquium, he mentioned that crossing symmetry could be broken in a theory with massive particles that jump from one vacuum to another. These Goldstone particles, they're like jumping infinitesimally from one vacuum to a nearby one. Could there be any issues with that?
Hopefully not. In my defense, I would say that here we are in a setup where low energy is essentially free, and so it's a controllable setup where we can check and do explicit computations.
Yeah, I mean, I agree it's quite different because you're not like hopping a large amount to another discretely separated vacuum, but I see I stimulated the question here.
I think to be precise, crossing is modified, right, not broken. So in this case, it's modified infinitesimally, and therefore it's not modified at all.
Are there any other questions? Okay, let's thank Alexandre for a great talk.